You're driving 200 miles an hour, your hands are trembling on the wheel, and you're watching a car pull away from you on the straightaway even though your engine is making more horsepower. How is that possible? Here's the thing. In racing, the fastest car doesn't always have the most powerful engine. Sometimes it has the smartest crew chief. And in NASCAR for over 7 decades, the battle between innovation and regulation has created some of the most mind-blowing engineering tricks in motorsport history. We're talking about modifications so brilliant, so perfectly executed, that NASCAR had no choice but to completely tear up the rulebook and start over. Some of these innovations came from backyard mechanics with nothing but intuition and a welding torch. Others came from million-dollar research programs at major automotive manufacturers. But they all share one thing in common. They changed NASCAR forever. This is legacy motoring, and I spend way too much time thinking about the genius innovations that changed racing history. If you're someone who appreciates the brilliant minds that push technology forward and loves the cat and mouse game between racers and regulators, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now, before we dive into these game-changing tricks, I want you to understand something. This isn't about cheating. Look, I know that's what some people will say, but here's what most people don't realize. Most of these innovations were completely legal when they were introduced. The teams found loopholes, gray areas, and unwritten assumptions in the rulebook. They exploited physics and engineering principles that nobody had considered before. They weren't breaking the rules, they were rewriting what was possible within them. And that's what makes these stories so fascinating. NASCAR would inspect these cars, measure them, test them, and pass them as legal. Then they'd watch them dominate on track and realize that something fundamentally game-changing was happening. Only after months, sometimes years, would officials figure out what was going on. And when they did, the response wasn't just a small rule tweak. It was comprehensive regulation that reshaped entire technical categories. According to research from the SAE International Journal of Engines, NASCAR's rulebook has grown from a simple 12-page document in 1948 to a comprehensive technical manual exceeding 250 pages today. And a significant portion of that growth came directly from the innovations we're about to discuss. Each trick will cover force NASCAR to add new inspection procedures, new measurement standards, and new technical specifications. Some added entire sections to the rulebook. The most impactful ones changed how NASCAR approaches regulation entirely, shifting from reactive enforcement to proactive control of every component on the car. Here's where it gets really interesting. Many of these innovations came from the same few brilliant minds. Smokey Yunick, Henry Smokey Yunick to be precise, was responsible for at least a quarter of all major NASCAR rule changes between 1950 and 1980. Junior Johnson, another legendary name, forced regulation changes through sheer creative thinking about vehicle dynamics and aerodynamics. These weren't just mechanics, they were engineers, physicists, and creative problem solvers who happened to work in racing. And the innovations they developed in the high-pressure world of NASCAR competition often found their way into production vehicles years later. Anti-lock braking systems, advanced aerodynamics, fuel injection optimization, tire compound development, all of these technologies benefited from racing innovations that started as ways to gain competitive advantage on the track. Now, you might be thinking, if these tricks were so effective, why don't we see them in racing today? That's exactly the point. We don't see them because they worked too well. They created such significant performance advantages that NASCAR had to eliminate them to maintain competitive balance. This is the paradox of innovation in spec racing series. The sport needs innovation to drive technology forward and keep manufacturers engaged. But too much innovation creates runaway advantages that make racing less competitive. Finding that balance has been NASCAR's central challenge for its entire existence, and the 10 innovations we're about to discuss represent the moments when that balance tipped too far toward innovation and had to be pulled back. Let's start with something that seems almost comically simple, but was absolutely genius in its execution: the extended fuel line trick. In 1966, a crew chief named Smokey Yunick arrived at Daytona International Speedway with a Chevrolet Chevelle that ran in the modified division. The car looked normal, sounded normal, and performed well but not suspiciously well during practice sessions. Then the race started, and something strange happened. Every car in the field was making pit stops for fuel at predictable intervals based on fuel consumption calculations that teams had refined over years of competition. But Yunick's Chevelle kept going, and going, and going. It would run an extra 10 laps, sometimes 15, beyond when it should have run out of fuel. Other teams were baffled. They checked their own fuel consumption numbers, they monitored Yunick's lap times to see if he was conserving fuel by running slower, but his pace was competitive, sometimes even aggressive. Where was this extra fuel coming from? NASCAR officials were equally confused. They inspected the fuel cell during pre-race tech inspection and found it to be the regulation size, exactly 22 gallons as specified in the rulebook. They looked for hidden auxiliary tanks in the chassis, in the body panels, anywhere fuel could be stored. Nothing. The car passed every single technical inspection without issue. This went on for several races. Yunick's cars would consistently run longer on fuel than physics suggested should be possible. Competitors complained, officials investigated, but nobody could find anything illegal. The car's fuel capacity was legal, it wasn't getting fuel from anywhere else, and yet somehow it was completing more laps per tank than identical cars with identical engines. Then came a particularly thorough post-race inspection after Yunick's car had finished well, and officials decided to drain the fuel system completely to verify the tank capacity. They drained 22 gallons from the fuel cell, confirming it was the legal size. Then, just to be absolutely certain, they told Yunick the car couldn't possibly run without fuel and asked him to explain his secret. Here's where Smokey Yunick became a legend. According to multiple accounts from people who were there, Yunick smiled, climbed into the completely empty race car, fired up the engine, and drove it out of the inspection area across the garage and back to his transporter, a distance of several hundred feet. The inspectors stood there with their mouth open, watching a car with an empty fuel tank drive away under its own power. The secret was brilliantly simple. NASCAR's rulebook specified the maximum size of the fuel cell, 22 gallons. It specified where the fuel cell had to be located. It specified the type of fuel that could be used, but it said absolutely nothing about the fuel line, the hose that carries fuel from the tank to the engine. Yunick had installed a fuel line that was nearly 11 feet long and had a diameter of approximately 2 inches. Now, a normal fuel line might be 6 feet long with a half-inch diameter, just enough to carry fuel from the tank to the carburetor. But Yunick's fuel line was a completely different beast. By making it 4 times as long and 4 times as wide, he'd essentially created a second fuel tank hidden in plain sight throughout the car's chassis. The math is straightforward, but the implications were revolutionary. A 2-inch diameter line that's 11 feet long has a volume of approximately 5 gallons. 5 additional gallons of fuel that technically wasn't in the fuel tank, so it didn't violate the tank size rules. 5 gallons that inspectors never thought to measure, because who measures the fuel line? At racing speeds with 1960s engine technology, 5 extra gallons translated to approximately 25 to 30 additional miles of range. That's exactly the advantage Yunick's cars were showing, an extra 10 to 15 laps at a typical speedway before needing to refuel. But here's what makes this truly genius. The fuel line was coiled and routed through areas of the chassis where it looked like normal component plumbing. It ran along frame rails, through the interior, behind body panels, carefully positioned so that it didn't look unusual during visual inspection. The connections were professional, the line itself was high-quality racing equipment, and everything appeared completely normal unless you specifically measured the internal volume of the fuel delivery system, which nobody had ever thought to do because it had never been an issue before. When NASCAR officials finally understood what Yunick had done, their reaction was a mixture of frustration and grudging admiration. This wasn't technically cheating, it was creative interpretation of the rules. The car's fuel capacity, as defined by the rulebook, was legal. Yunick had simply found capacity in a place nobody had thought to regulate. The immediate response was a rule change specifically addressing fuel line dimensions. NASCAR mandated maximum fuel line lengths, maximum diameters, and specific routing requirements. They added new inspection procedures that included measuring fuel system components. They even specified the type of fittings that could be used to prevent teams from hiding volume in oversized connectors. But the deeper impact went far beyond fuel lines. This single innovation changed NASCAR's entire approach to writing technical regulations. Before Yunick's fuel line trick, NASCAR rules tended to be relatively simple. Here's what you can't do, everything else is fair game. After the fuel line incident, NASCAR realized they needed to flip that approach. Instead of prohibiting specific things, they needed to explicitly define what was allowed and prohibit everything else. Every component needed specific dimensional requirements, every system needed defined parameters, and inspection procedures needed to verify not just major components, but every single part that could potentially provide an advantage. According to Yunick's own later accounts, and he loved talking about his innovations after they'd been banned, the fuel line was just the most obvious trick on that car. He claimed there were at least a dozen other modifications that provided competitive advantages, some of which NASCAR never discovered. He talked about creative interpretations of engine displacement rules, suspension modifications that technically complied with the regulations but provided handling advantages, and aerodynamic tricks that were invisible to the naked eye. Yunick estimated that if NASCAR had found every innovation on that Chevelle, he would have been banned from the sport for life. But they only caught the fuel line, and even that took them months to figure out. The fuel line trick has become legendary in NASCAR history, one of those stories that gets told and retold whenever people discuss the sport's creative rule-bending era. It represents a time when individual mechanical genius could create significant competitive advantages through pure creative thinking. Today, that's virtually impossible. Modern NASCAR fuel systems are completely specified. Teams must use fuel cells from approved manufacturers. Fuel lines are limited to specific lengths and diameters, and every component is inspected with precision measuring equipment. The detailed fuel system regulations in today's NASCAR rulebook, which span multiple pages and specify everything from vent line routing to filler neck design, exist almost entirely because Smokey Yunick decided to turn a fuel line into a fuel tank. This innovation perfectly sets the stage for understanding the 10 game-changing tricks we're exploring. It wasn't about cheating. It was about seeing possibilities that nobody else saw, exploiting gaps in regulation that existed because nobody had thought to close them, and pushing the boundaries of what was technically legal until NASCAR had no choice but to rewrite the rules. Now, let's move into something that fundamentally challenged what a race car could be: asymmetrical engineering. See, every production car you've ever driven was designed with bilateral symmetry. The left side mirrors the right side. This makes sense for street cars because they need to turn both directions equally well. But here's the thing about NASCAR. The cars only turn left. Every corner at every oval track in the series goes the same direction. So why would you build a symmetrical race car? Banjo Matthews asked that question in 1971 and came up with an answer that nobody had considered. What if you shifted the entire chassis slightly to the left, moving the weight distribution toward the inside of every corner? The concept seems obvious in hindsight, but implementing it required engineering precision that was remarkable for the era. Matthews didn't just slap some ballast on one side of the car. He fundamentally redesigned the relationship between every component and the center line of the vehicle. The driver's seat moved left by about 3 inches. The engine mounting points shifted so the heavy V8 sat slightly off-center. The transmission tunnel was relocated. The fuel cell positioning changed. Every heavy component that could be moved was repositioned to put more weight over the left side tires, exactly where you need traction when turning left at 150 miles per hour. From 20 feet away, the car looked completely normal. The body panels were standard, the paint scheme was typical, and nothing seemed unusual. But underneath that conventional exterior, the entire mechanical package was biased toward left-hand cornering. The performance advantage was immediate and significant. Matthews's cars could carry more speed through corners because the left side tires had better grip from the additional weight pressing them into the track surface. They could brake later going into turns because the weight distribution matched the deceleration forces during left-hand entries. They could accelerate earlier exiting corners because the left rear tire had more traction. On short tracks like Bristol and Martinsville, where cornering performance matters more than straight-line speed, Matthews's offset cars were nearly untouchable. Other teams spent months trying to figure out what was different. They suspected engine modifications, they looked for illegal aerodynamic tricks, they even accused Matthews of using special tires. The idea that the fundamental architecture of the chassis could be altered never occurred to most competitors because it violated the basic assumption that race cars should be symmetrical. NASCAR officials were equally stumped. They measured ride height, legal. They checked engine specifications, compliant. They verified body dimensions, standard. The car passed every inspection because there was no rule requiring bilateral symmetry. The discovery came almost by accident during a detailed post-race inspection focused on a completely different suspected violation. An inspection was measuring distances between body panels and frame rails, looking for evidence of illegal body modifications, when he noticed the numbers didn't match side to side. The left side measurements were consistently different from the right side. Not by much, maybe 2 or 3 inches, but consistently different across every measuring point. Once officials knew what to look for, the entire trick became obvious. NASCAR's response was comprehensive. They created centerline reference requirements that mandated symmetrical chassis construction. They developed new inspection procedures using centerline jigs that could detect offset frames instantly. They specified that major components like engines and fuel cells had to be positioned symmetrically within defined tolerances. They even regulated driver seating position to prevent teams from using the driver's body weight as a left side bias tool. The rulebook expanded by over 20 pages just to address chassis symmetry, creating technical specifications that hadn't existed before Matthews proved they were necessary. But here's where it gets really interesting. Matthews' innovation didn't disappear entirely. Modern NASCAR Cup Series cars use carefully regulated weight distribution that still biases toward left side heavy, just within strictly defined parameters. The insight that asymmetrical weight distribution improves oval track performance was absolutely correct. NASCAR simply had to control how much asymmetry was allowed, rather than leaving it unlimited. Today's inspection procedures can detect weight distribution variations of less than 1%, and teams spend enormous resources optimizing within the allowed parameters. The foundation for all of that precision came from Banjo Matthews deciding that if the car only turns one direction, it should be built for that direction. Moving from chassis engineering to something that seems almost primitive by today's standards, but was revolutionary in its time, body panel manipulation through chemical treatment. In the late 1960s, someone discovered that you could reduce the thickness of sheet metal by submerging it in acid. The process was straightforward but required careful execution. You'd take a standard steel body panel, hood, roof, door, whatever, and submerge it in an acid bath for a precisely measured time. The acid would eat away at the metal from both sides simultaneously, reducing thickness while maintaining the panel's shape and external appearance. The weight savings were dramatic. A factory hood that weighed 40 pounds could be reduced to 20 pounds. A roof panel could lose 15 pounds. Quarter panels, trunk lids, door skins, everything made of sheet metal could shed significant mass. Do this to every body panel on a race car, and you could remove 150 to 200 pounds from the vehicle's total weight without any visible modification. The car looked completely stock, passed visual inspection, and even sounded normal when you tapped on the panels because the outer surface remained intact. Now, you might be thinking this sounds incredibly dangerous, and you'd be absolutely right. Acid-dipped panels had significantly reduced structural strength. In a crash, they would crumple and tear much more easily than standard panels. The protection they offered drivers was compromised. But in an era before comprehensive crash testing and modern safety requirements, teams were willing to accept that risk for competitive advantage. Weight is everything in racing. A 200-pound reduction translates to faster acceleration, better braking, and improved handling. At high speeds, it can mean tenths of a second per lap, which over a 500-mile race adds up to significant gains. The trick stayed hidden for years because there was no obvious way to detect it. Visual inspection showed normal-looking panels. The car met all dimensional requirements. Even experienced inspectors couldn't tell the difference just by looking. The discovery happened at the 1969 running of the first Talladega 500 when a post-race inspection got more physical than usual. An official, reaching into a wheel well to check something else entirely, accidentally pushed too hard against a door panel. His thumb went straight through the metal like it was aluminum foil. The panel that should have been able to support a person's weight collapsed under the pressure of a single finger. Further investigation revealed the extent of the problem. Multiple cars in the top finishers had acid-treated panels. Some had been dipped so aggressively that the metal was barely thicker than paper. The competitive advantage had been so significant that once one team figured it out, the knowledge spread rapidly through the garage. NASCAR's response introduced entirely new concepts to race car inspection. They established minimum thickness requirements for all body panels. They brought in ultrasonic testing equipment that could measure metal thickness without damaging the surface. They developed sampling procedures, where small sections of panels could be removed and measured. They created chain of custody requirements for body panels, tracking them from approved manufacturers to installation. The acid dipping era lasted only about 18 months once NASCAR started actively looking for it, but its impact on inspection procedures was permanent. The concept that teams might modify the fundamental material properties of components, not just their shape or position, was revolutionary for NASCAR enforcement. It opened inspectors' eyes to an entirely new category of potential modifications. Today, body panels for Cup Series cars come from approved suppliers with documented material specifications. Random destructive testing verifies that panels meet thickness requirements. The sophisticated material verification procedures used in modern NASCAR inspection trace directly back to someone deciding that if you can't use lighter materials, you can use less of the materials you have. This brings us to one of the most sophisticated chemical modifications in NASCAR history: tire treatment. The rubber compounds used in racing tires are incredibly carefully engineered. Goodyear spends millions developing compounds that balance grip, durability, and consistency for specific track conditions. The tire compound for Daytona is different from Bristol, which is different from Martinsville. Every track gets tires optimized for its unique characteristics. But what if you can modify those carefully engineered tires to get even more grip? In the late 1980s, someone discovered that certain chemical solvents could penetrate racing tire rubber and soften it significantly. The process was called tire soaking, and it became one of the most widespread cheating scandals in NASCAR history. Teams would take their allocated tires and submerge them in chemical baths for days before a race. The solvents would penetrate the rubber compound, making it softer and stickier than Goodyear intended. The treated tires looked identical to normal tires, felt similar to the touch, and passed visual inspection without issue. The performance advantage was enormous. Softer tires provide more mechanical grip because the rubber conforms better to track surface irregularities. A car on soaked tires could carry significantly more speed through corners, brake later, and accelerate harder. We're talking about lap time improvements of a full second or more, which in professional racing is an eternity. The chemicals used were industrial solvents: toluene, xylene, various benzene derivatives. These are not substances you want anywhere near human skin, and garage personnel handling treated tires were being exposed to serious health hazards. The smell in some team shops was reportedly overwhelming. NASCAR knew something was wrong, but couldn't prove it for months. Traditional tire inspection methods showed nothing unusual. Hardness testing with durometers sometimes caught treated tires, but teams learned to soak tires to specific levels that would still pass basic hardness checks while providing significant grip advantages. The breakthrough came when NASCAR brought in a chemist who suggested gas chromatography testing, a technique that could identify foreign chemicals that had been absorbed into the rubber compound. When they started testing tires this way, they found contamination everywhere. The response was the most comprehensive tire regulation system in motorsport's history. NASCAR took complete control of the tire supply chain. Teams no longer received tires at their shops. Instead, Goodyear delivered spec tires directly to the track on race weekends. Every tire was coded, logged, and tracked from manufacturer to mounting. Random tires were pulled for laboratory testing throughout race weekends. Teams couldn't even take used tires home for analysis. All rubber stayed under NASCAR control. Chain of custody documentation rivaled evidence handling in criminal investigations. The tire soaking scandal lasted less than 2 years once NASCAR implemented comprehensive testing, but it fundamentally changed the relationship between teams and their equipment suppliers. NASCAR realized that when the stakes are high enough, teams will modify anything in search of advantage, including components that come from outside suppliers. The solution was to take control of critical components entirely, removing teams from the supply chain for items where modifications could provide unfair advantages. Today's spec tire system, with its barcodes and laboratory testing and strict custody requirements, exists because someone figured out that the right chemicals could make rubber do things it wasn't designed to do. Now we arrive at the innovations that didn't just bend the rules, they broke NASCAR's fundamental understanding of what a stock car should be. And nothing represents this more dramatically than the aerodynamic revolution that forced NASCAR to completely redefine the sport's identity. Junior Johnson was watching wind patterns one afternoon in 1965 when something clicked in his mind. Every other team was obsessing over cubic inches and carburetor jetting, chasing horsepower like it was the only variable that mattered. But Johnson realized something profound. At 180 miles per hour, air resistance increases exponentially. A car making 550 horsepower that moves cleanly through the air will beat a car making 600 horsepower that's pushing against aerodynamic drag. The math was undeniable once you understood the physics. Johnson started making modifications that were invisible to casual observation. The windshield angle changed by just 3 degrees, imperceptible unless you were specifically measuring it. The roofline dropped by less than an inch, maintaining the visual profile of a stock Chevelle while reducing frontal area. The rear window transition was smoothed to help air reattach to the body after passing over the roof. Each individual change was tiny, but combined they reduced aerodynamic drag by nearly 15%. The results were immediate and confusing to competitors. Johnson's cars were consistently faster on straightaways, despite dynamometer testing showing his engines made less power than the competition. He could run flat out in sections of track where other drivers had to lift. In drafting situations, his cars would pull away when they should have been evenly matched. Teams accused him of illegal engine modifications, fuel additives, even sabotage. Nobody suspected the body because it looked completely stock. When NASCAR finally discovered the modifications during a detailed postseason teardown, they realized they had no tools to measure what Johnson had done. There were no templates checking windshield angles, no specifications for roof curvature, no standards for rear window shape. Johnson had exploited a massive blind spot in technical inspection. NASCAR's response created the template system that still exists today. Metal cutouts that verify every curve and angle of the body meets exact specifications. What started as checking a few key dimensions evolved into comprehensive verification of the entire vehicle shape. But Johnson's aerodynamic tricks were subtle refinements compared to what came next. In 1969, Chrysler Engineering decided to stop pretending that stock car racing had anything to do with stock cars. They built the Dodge Charger Daytona, a machine that looked like it belonged on a different planet. The nose cone extended nearly 2 feet beyond a standard front bumper, shaped by wind tunnel testing to slice through air with minimal resistance. The rear wing stood almost 2 feet above the trunk lid, mounted on massive aluminum struts, generating downforce that pushed the rear tires into the track surface with hundreds of additional pounds of pressure. When the Daytona appeared at Talladega for its competition debut, other teams literally stopped working to stare. Nothing like this had ever been seen in NASCAR. The car qualified at 199.466 miles per hour, shattering the existing track record by nearly 15 miles per hour. It wasn't just faster than the competition, it was operating in a completely different performance envelope. The aerodynamic efficiency was so high that the Daytona could run flat out on straightaways where conventional cars had to lift for stability, then carry more speed through corners because the wing kept the rear end planted. Plymouth responded with the Superbird, an even more refined version of the same concept. These winged warriors, as they became known, dominated superspeedway racing throughout 1969 and 1970, with a level of superiority that threatened the sport's existence. Ford and General Motors demanded NASCAR take action, threatening withdrawal if the aerodynamic arms race continued. Track owners expressed safety concerns about cars approaching 210 miles per hour on facilities designed for 180. Insurance providers questioned whether their coverage was adequate for these speeds. NASCAR faced an existential choice. They could allow unlimited aerodynamic development, which would require every manufacturer to spend tens of millions on wind tunnel programs and potentially price smaller teams out of competition entirely, or they could restrict the technology and return to something resembling the stock car racing concept the sport was founded on. They chose restriction, implementing rules that limited engine displacement in aerodynamic cars while allowing larger engines in conventional bodies. The winged cars were effectively legislated out of existence. This decision shaped NASCAR's regulatory philosophy for the next 50 years. The sport would allow innovation, but only within carefully controlled parameters. Aerodynamic development would be permitted, but restricted to prevent runaway advantages. Manufacturers would compete, but the playing field would be deliberately leveled to maintain close racing. The Winged Warrior era proved that unrestricted innovation could produce amazing technology, but terrible competition. The restrictor plate regulations that followed illustrated this philosophy perfectly. When speeds at Daytona and Talladega continued climbing through the 1980s, NASCAR mandated metal plates that limited airflow into engines, reducing horsepower and speeds. Every team had to use identical plates, theoretically equalizing performance. But crews immediately started finding ways around the restriction. Some drilled microscopic holes through the plates, so small they were invisible but collectively flowing significant extra air. Others developed plates from alloys that expanded when heated, opening up the restriction as engines reached operating temperature. The most sophisticated modifications used memory metals that changed shape under specific conditions. At inspection temperatures, the plates met specifications perfectly. But once installed in a hot engine, the material would deform slightly, creating gaps that didn't exist during testing. NASCAR estimated that illegal restrictor plate modifications provided advantages of 15 to 40 horsepower, massive gains in a formula where everyone theoretically had identical engine restrictions. Catching these modifications required NASCAR to take complete control of restrictor plate manufacturing and distribution. Plates were manufactured to precise specifications, serialized individually, and distributed to teams just before qualifying. Tamper-evident seals prevented unauthorized access. Post-race plates were impounded immediately and subjected to laboratory analysis. The level of control was unprecedented for a simple piece of perforated metal, but the competitive advantage from even minor modifications justified the effort. Looking across all these innovations, a clear pattern emerges. NASCAR's rulebook grew not from theoretical planning, but from practical experience with creative rule interpretation. Every new regulation chapter traces back to someone who found a loophole and exploited it successfully enough that officials had to respond. The comprehensive body templates exist because of aerodynamic modifications. The material specifications exist because of acid-dipped panels. The tire custody procedures exist because of chemical treatments. The fuel system regulations exist because of Smokey Yunick's fuel line. Today's NASCAR Cup Series cars are the most heavily regulated vehicles in motorsports. Every component is specified, measured, and verified. Teams operate within parameters so tight that advantages come from tenths of percentage points rather than revolutionary innovations. The era of game-changing tricks that force wholesale rule changes has essentially ended, replaced by an environment where compliance is mandatory and variation is minimized. Whether this evolution improved the sport or diminished it remains a topic of passionate debate among fans and competitors alike. But those legendary innovations, the fuel lines and offset chassis and winged warriors, they represent something that modern racing has largely lost: the triumph of individual creativity over institutional control. For a few decades, brilliant mechanics and engineers could outthink the rulebook, finding advantages that nobody had imagined possible. Their innovations were so genius that NASCAR literally had to change its laws, and that's a legacy worth remembering. If you enjoyed this exploration of racing innovation, drop a comment telling me which trick impressed you most. Hit subscribe for more deep dives into motorsports history, and I'll see you in the next one.